and he will tell, our speaker is Professor Mohammed Sabak, and he will tell us about a new polynomial for checkerboard-colorable four-valent graphs and the Jones polynomial. Let's welcome.
Thank you. Thank you very much. I thank the organizers for giving me the opportunity to give this talk. This talk will be entitled A New Polynomial for Checkerboard-Colorable Four-Valent Virtual Graphs in the Jones Polynomial. So this is a joint work with Professor Hamid Abshir from the University of Hassan II, Morocco, and Professor Khalid Kazakzeh from the Yarmouk University, Erbil in Jordan. So in this talk, we will be looking at four-valent checkerboard colorable virtual graphs. Then we will define a new polynomial for them. Then we will recover the Jones-Kaufman polynomial for checkerboard colorable links from the polynomial for graphs that we define.
I think a checkerboard-colorable is the same as alternatable, right?
Yes, for links. Yes, exactly.
Yeah, okay.
Okay, so the Jones-Kaufman polynomial is an invariant of oriented virtual links. It was introduced by Kauffman, and it was inspired by its previous work together with the work of Jones. There have been a lot of combinatorial formulation for this polynomial through the years. The first attempt was by Thistlethwaite in the late 80s, where he gave an expression of the Jones-Kaufman polynomial for classical links using an enhanced version of the tooth polynomial. Then after that, in the late 2000s, there were a lot of works that dealt with this combinatorial approach of the Jones-Kaufman polynomial, this time for virtual links. And the authors used this time the Bolo-Basser-Jordan polynomial, which is a polynomial that is defined for Riemann graphs. In 2017, Deng, Jin, and Kaufman introduced a new polynomial for a new type of graphs, namely the cyclic graphs, and they showed that this polynomial is related to the Jones-Kaufman polynomial and enabled them to recover it and have a new formulation of it. So in this talk, we will give a similar approach in the sense that we are going to define a new polynomial for checkerboard colorable virtual graphs. And then we will recover the Jones-Kaufman polynomial from that polynomial. Okay, so let's start talking about four-valent checkerboard colorable virtual graphs. So a four-valent virtual graph is a four-valent connected graph in the plane, and we will have two types of double points: the actual double points, which are the vertices, and the other double points, which called virtual double points, and an edge in such a graph will be a curve that joins two consecutive vertices. When we have such a graph, we say that it is checkerboard colorable. If there is a color in one side of each edge in the graph, such that near a vertex the color of opposite edges alternates, and near a virtual double point the coloring go through, independent of the crossing strand in its color. So we have here an example of a checkerboard colorable graph. So there is a topological description of checkerboard colorability. So if we have a graph, then we say that it is checkerboard embeddable in some orientable surface sigma. There exists an embedding of G in sigma such that the complement of G in sigma consists of two cells and such that these two cells can be colored by two colors, say black and white, such that each two components of the complement of G in sigma, which are adjacent by an edge of G, have always distinct colors. So Montirov showed that a graph is checkerboard colorable if and only if it is checkerboard embeddable in some orientable surface. So this checkerboard embeddability actually can be formulated into homological means. So there is actually an equivalence between being checkerboard colorable and the fact that when we embed G in an orientable surface, then the natural inclusion of G in sigma induces the trivial homomorphism in the homology with Z2 coefficients. So now we will add orientations to the edges so that we get the graphs or 2D graphs, meaning that at each edge we will have two incoming and two outgoing edges. So this is what we call a 2D graph.
Yeah, we call it source sync. Yeah, source sync. Yeah, source target. Yeah. Okay. Yeah.
Yeah, so for the source target structure, it is a special case of 2D graphs where we have
Why special? Why special? Isn't it the same?
no, because here I agree that this has a source target structure, but for 2D graphs in general, it is not. We can have something like this, for instance. We can have something like this, say something like this, which is not exactly source target structure, but nevertheless, it is still a 2D graph. So it is still at the vertex, we have two incoming and two outgoing edges. But it is not a source target structure. So a source target structure,
The two incoming and the two outcoming are not adjacent.
yes,
For two diagraph, they are not necessarily adjacent.
yes, yes. So the source target structure, it's an orientation of the edges of the graph such that we have these two types of orientations at each vertex. So here we have an example here. So as we can see at each vertex, we have this configuration at the left. So there is an equivalence between the existence of a source target structure and the checkerboard colorability. And we can actually, for each checkerboard coloring, fix a source target structure by this convention here. So let's say that we have here a source target structure. Then we can assign to it a checkerboard coloring by putting the checkerboard coloring at the left of the oriented edge. And conversely, if we have a checkerboard coloring, then we can convey that the source target structure is chosen so that the checkerboard coloring comes at the left of each oriented edge. Okay, so now we will define Euler circuits. So an Euler circuit of a digraph is a path that satisfies the following. First, it begins in ends at the same vertex, which means that it is a closed loop. Then it must traverse each directed edge of the graph exactly once. So here I highlighted the Euler circuit here. So as you can see, I have put some labelings on the edges. So successively, when we traverse along the Euler circuit, so you will go through E1, the first edge, E2, E3, etc. So we can write this Euler circuit gamma as an alternating sequence of vertices and edges like this.
So do you rotate at each vertex? Is it a rotating circuit, or does it go straight, or does it rotate?
No, it follows the direction of each edge. So here, if you look at E1, it will go E1, then E2.
Yeah, so you rotate, right?
That's exactly. Yes, exactly.
Okay.
So at each
So I
vertex,
call it rotating circle. So there can be some difference in notation.
yes, of course. So at each vertex V, since you have a source target structure, then two opposite edges here will be incoming and two will be outcoming. Then you have uh, this possible path, then this one, or else you will have this one and this one. So like this.
Sorry, I came in late. I just have a question regarding the
Yes.
vertices. Are they commutative? Are the directions, do they matter, or do they refer to the same vertex?
No, the directions doesn't do not matter, but uh, when you choose starting points, say V1, then you have your starting point in the sequence. If you change the starting point, it will be just a cyclic permutation of this.
So it's commutative?
Mm,
Not. It's not commutative. Okay.
it's not commutative. It's not commutative. It's just a matter of so for notating gamma, you must choose a starting point. I started here with V1, but if you change the starting point, you are going just to do some cyclic permutation of this.
Okay, thank you.
You're welcome. Okay. So a D graph is said Eulerian if it has an Euler circuit. So following theorem is a classical theorem. I found it in a paper by Aratia, Bolobas, and Sorkin. So they say that a D graph is Eulerian if and only if the number of incoming and outgoing edges at each vertex are equal. So in particular, since checkerboard-colorable graphs are 2D graphs and they have a source target structure, so they are two in, two out graphs, which mean that they are Eulerian, and each Euler circuit visits each vertex exactly twice. Okay, so now we will introduce the polynomial. So first of all, we are going to introduce this concept of merging. And before this, we are going to consider vertex-signed checkerboard-colorable 2D graphs, which mean that we are going to add some signs to the vertices. So each vertex will carry a sign plus or minus. And here at the left of the slide, you will see that I have some, here I have some Euler circuits, and I have some vertex here, V. Let's say this is how V shows up in the alternating sequence that is the Euler circuit. So the first appearance of V, we have an edge A before V, then an edge D after V. So this is the first visit of the vertex V. So here actually we are coming from A to B. Sorry, from A to D. And in the second visit, we come from C towards B. So if we are in this case, and if we have a positive vertex, then here we do what we call the merging operation, which consists in deleting the vertex V and connecting A with D and B with C. And we choose to add a marker here, this little chord here, and label it capital A. So if we are still in this case, but this time we have a negative vertex, then we merge and we put a capital B marker. So now let's look at the second case, where at the first visit we go from A to D here. Sorry. But here the checkerboard coloring, as you can see, comes from the sides. So in this case, if we have a positive sign, then we put a little a letter for the marker labeling. And if we have a negative sign, we'll put a little b marker. So if we merge at each vertex, if we merge an Euler circuit at each vertex, then we get what we call the state of the Euler circuit. So here I have the Euler circuit gamma from earlier, and here I have the gamma state with its four markers labeled accordingly. So in addition to the state, we can associate to an Euler circuit what is called a chord diagram. So it is actually very simple. So you take a circle and you put two unevenly spaced points around its circumference. Then you start traveling the Euler circuits, following the orientation of the edges, and you start from any vertex. Then you start labeling each of the two endpoints on the circle successively with the label of each visited vertex. So since the Euler circuit visits each vertex exactly twice, then the vertex will appear twice at the circumference of the circle. Once this is done, we are going to join the 2 points that correspond to the same vertex by a chord, and we make sure that each pair of chords intersect at most once, and no more than 2 chords intersect at the same point. So here I have the example from earlier. Here I have gamma, the Euler circuit, and here I have C of gamma, the chord diagram. So if you start from V1, let's say, so the first encountered one, sorry, you start from, yes. So V1, V2, yes, start from here. So V1, then V2, then V4, I guess I have a little typo here. So let's say I have V1, I go through E1 to V2, sorry, this is V2, then V4, then V3, then V2, etc. Yes. So I must put, okay. So using the Using the chord diagram, we are going to define the states of a vertex with respect to an Euler circuit. So, if we have two vertices, Vi and Vg, we say that they interlace in the Euler circuit gamma if the corresponding chords intersect in the chord diagram. So, for instance, here, the chord of V1 intersects with the chord of V2, so we will say that V1 and V2 interlace in gamma. So we fix an order on vertices, of course, and we will say that a vertex Vi is dead with respect to gamma if it interlaces with another vertex Vj, so that j is less than e. Otherwise, the vertex Vi is live. So here in this example, V1 is live, of course. It is the lower labeled vertex. It will always be live. You can see here that V1 and V2 intersects, they interlace. So this means that V2 is dead. Here we can see that V3 only intersects or interlace with V4, which means that V3 is live. And here we can say that V4, for example, interlace with V2, so V4 is dead. So once we have an Euler circuit and its states together with their chord diagram, then we can define an activity letter, let's say Wi of gamma, that will be assigned to the vertex Vi. So this letter will be picked up from this alphabet here. We have L, capital and little, D, capital and little. We have the overlined ones here. So the rules for choosing this letter are expressed in this table. So if Vi is live with respect to gamma, then the letters will be L letters. And if we have capital A for the marker in the states corresponding to Vi, then we will choose capital L. If we have a marker labeled B, capital B, we will have L bar, etc. So this will give us what we call the activity word of gamma, of the Euler circuit gamma, which will consist of the n letters. So each letter corresponds to a different vertex. And n is, of course, the number of vertices. So here we have the example from earlier. So V1 is live, V2 is dead, V3 is live, and V4 is dead. And the marker for V1 is a little a marker. So we have a little L for V1. For V2, we have a capital A marker, and it is dead. So we have capital D. For V3, it is a little b marker, and it is dead. So sorry, here I must put yes. Sorry, of this must be L D L bar D bar. So this is the correct one. I have here a typo. So because V3 is live, and for V4 is dead with the capital B marker, so it's capital D bar. Okay. So once the activity word is written, then we will assign to each letter a monomial called the weight of the vertex Vi. So the rules of choosing this monomial are expressed in this table. So afterwards, we will get the weight of the Euler circuits, mu gamma, which is just the product of all the monomials corresponding to each letter. So here for little l, we have minus q to the power of 3. For d, we have q. D bar, we have q. And for capital D bar, we have q minus 1. So the weight of this Euler circuit gamma is minus q to the power of 4. Okay, so now we will define the polynomial. So the polynomial x associated to g, the determinant q, is just the sum over all Euler circuits of the weights. So this definition here deals only with connected graphs. So here we extend the definition for non-connected or disconnected graphs. So if we have a graph G with connected component G1.
Excuse me, if
Yeah.
so where do minus q squared minus a to the minus 2 come from? So you define it according to the first formula, and where does the second formula come from?
Yes, so it is inspired by the definition of the Jones-Kaufman polynomial, because at the end, our main objective is to recover the Jones-Kaufman polynomial.
Right, but the question is, you gave the first definition. Now you say that the first definition will give you the second definition, right? And I don't see why it should be so.
I'm not actually saying that the first definition will give us the second definition. The second definition is, let's say, an extension of the first, in the sense that if you have a connected graph here, so this factor will not appear. So it will
Okay.
be, yes, yes. Okay. So here I have an example. So here I have a checkerboard for valence graph G. It has 9 Euler circuits. So I just gave the 9 chord diagrams, and we will have the activity letters written under each chord diagram, and we have the weights of each Euler circuit written here. So at the end, we will find minus q to the power of minus 7, minus q to the power of minus 3, plus q to the power of 5. So the main theorem is that if G is a vertex-signed checkerboard-colorable 2D graph, then the polynomial xg of q is an invariant of the graph isomorphism class of G, and it is independent from the chosen checkerboard colorant of G, because there are 2. And also it is independent from the chosen order of the vertices. So for the 2 first points, meaning that it is a graph isomorphism class, it is an invariant of the graph isomorphism class of G, and it is independent from the chosen checkerboard coloring. These 2 points are not complicated to prove. They are actually very easy to prove. So the only point that is a bit difficult to see is the last one, namely that x of G is independent of the chosen order. So how we went about it? Actually, we used what is called transpositions of the Euler circuit. which are operations which one can do on Euler circuits. So if Vi and Vg are interlacing in gamma, and if gamma is written as such, so let's say we have something here. This is a sequence, alternating sequence of edges and vertices. Then we have our first visit to Vi, then another sequence B, then our first visit to Vg, another sequence C, second visit to Vi, another sequence D, and the last visit of Vg. So what we will do is that we will take this and we just swap the letters B and D. We will get the transposition on the pair Vi Vg, which is denoted like this. So basically we are just moving this portion and this one, keeping A in its place, keeping C in its place. Okay, so there is actually a result saying that the Euler circuits of a 2D graph, or just of a D graph in general, are or make up for a single orbits under transposition, meaning that each two Euler circuits graph can be obtained from each other by some transposition. So we will denote by gamma index Ig the Euler circuit that is identical to gamma, except that we swap the labels of Vi and Vg. So here I have the general scheme here. So if we have the chord diagram of gamma, so we have A here, then Vi, then B, then Vg, then C, then Vi, then D. Then we will swap the places of B and D to get the transposition here. And for getting this guy here, actually what we do is that we swap the labels of Vi and Vg. So here Vi becomes Vg and Vg becomes Vi. And also this one will have its transposition. It doesn't matter here the order of the transposition, then the swap, and actually we can swap then transpose. Okay, so what we show that is that the weight of gamma will be equal to the weight of the swapping, and the weight of the transposition will be equal to the weight of the transposition after the swapping of labels. Or else, the weight of gamma will be equal to the weight of the transposition after swapping, and the weight of the transposition will be equal to the weight of the swapped version, which means that for each Euler circuit of the graph, we will have a single and a unique Euler circuit of the graph where we swap the labels of I and G with the same weight. And this will be sufficient to prove that the polynomial does not change if we change the order of the vertices, since changing the order actually is spanned by these swappings. Okay. So now we will see how to recover the Jones-Kaufman polynomial from the previously defined polynomial. So a quick reminder, quick recalling of definitions. So a virtual link diagram is an immersion of one or several circles in the plane with only double points. So we'll have two types of double points, classical crossings, so which are indicated, which are indicated by over and under crossings. And we will have second type of double points, which are virtual crossings indicated by the circles around them. So we will say that two virtual link diagrams are equivalent if they differ by a finite sequence of the generalized Westminster moves that are depicted here below. And virtual link is just an equivalence class of virtual link diagrams and is generalized with Westminster move. So the virtual links were introduced by Kauffman as a natural generalization of classical links. So we'll define skein triple as consisting of three diagrams D0, and D1, which are identical except in a small neighborhood of a classical crossing C. So outside this disk, the three diagrams are identical and they differ as depicted here inside the disk. So the Jones-Kaufman polynomial, or the Kaufman bracket polynomial is defined recursively by the three famous axioms. So here we have for the unknots without any crossings, it is 1. If we have a diagram D and we have a trivial circle disjoint from D, then the bracket is equal to the minus q to the power of minus 2 minus q to the power of 2 of the bracket of D. And if we have a skein triple D, D0, D1, then their brackets are related in this manner. So the brackets of D is equal to Q times the brackets of D0 plus Q minus 1 to the, multiplied by the brackets of D1. So this is the Kaufman brackets. And to recover the Jones-Kaufman polynomial, we need to define the right of an oriented virtual link diagram. So when we add the orientations, we'll have two types of crossings. Here we have positive crossings, negative crossings. And we define the right of D as being the number y of D, which is the number of positive crossings, minus x of D, which is the number of negative crossings. So the Jones-Kaufman polynomial, which is an invariant of oriented virtual links, is defined as minus q to the power of minus 3 right of D times the bracket polynomial of D. So it doesn't matter which link diagram we choose for the link L, since this polynomial will be invariant if we have equivalent diagrams. So now we'll look at checkerboard-colorable links, which are also called alternable links in some papers. So if we have a virtual link diagram, then we can get a 4-valence virtual graph from this diagram by replacing each classic crossing with a vertex and each virtual crossings by virtual double points. So here, as you can see, we have the classical crossings which become vertices, and for the virtual double points, virtual crossings, sorry, for the virtual crossings, we will have just virtual double points. Okay, so this is called the shadow graph of the diagram. So this is the shadow graph of D, and this is D. Okay, so if the shadow graph is checkerboard colorable, then we say that D is a checkerboard colorable link diagram. So checkerboard colorability of virtual links behave well under the generalized Ridgmeister moves, since there is a theorem by M that states that if we have two checkerboard colorable diagrams which are equivalent, then there exists a sequence of checkerboard colorable preserving Ridgmeister moves that go from one diagram to the other. A virtual link will be said to be checkerboard colorable if it admits a checkerboard colorable diagram. So this notion of checkerboard colorable links was introduced by Kamada. Okay, so now let's see how we can turn a checkerboard colorable virtual link diagram into a vertex-signed checkerboard colorable virtual graph. So we have here the rules for assigning the signs to the vertices. So we have 4 different possible configurations, and these are all the possible configurations, and we listed for each configuration which sign to choose. So here I have this example here. So if you look at this crossing, for instance, it will be a negative vertex here. And this one will be a positive vertex here. Okay, so at the end, if we have a checkerboard colorable virtual link diagram, then we can get a vertex-signed checkerboard colorable 2D graph. Okay, so now we are going to explain how the two polynomials are related. So if L is an oriented checkerboard colorable virtual link, and G is the vertex-signed shadow graph of L, then the Jones-Kaufman polynomial of L is equal to minus q to the power of minus 3 the right of L times the polynomial x of G. So for the proof, actually, it's very simple. So we have that the bracket polynomial of the circle is 1. And we have that the bracket polynomial of t is q times the bracket polynomial of d0 plus q minus 1 d times the bracket polynomial of d1. So where d is like this, d0 is this one, and d1 is this one. So what we do is that we show that if we have a graph G, say G, we have G like this, and we have a positive vertex V. Then we merge at V and we get two graphs with one less vertex. So look at this one and this one. And we show that we have actually the same skein relation, which means that this one will be equal to Q of G0 Q plus Q minus 1 X G1. And of course, by the rules of assigning the signs to the vertices, this crossing will correspond to this sign for the vertex. And at the end, if we compare the two scanulations, we will get the results quite easily. Okay. So now we'll discuss a little remark that we made from our work. So the remark is about the alternateness of the Jones polynomial for alternating virtual link. So we know that if L is a classical alternating link, then it's Jones polynomial. If it's written like this, it's a sum of coefficients AI q to the power of I. Then by results of Tisler weights, we have that this polynomial is alternating, meaning that minus 1 to the power of I plus j times the product of the two coefficients AI, AJ is always bigger than 0. So this is true in the classical case. So this property actually does not generalize to the virtual case. In a paper by Boudin and Karimi, we find this example here. So this knot, which is 52426, this is a reference of the knot in the tables made by Boudin and Chrisman. Here is the link here. So this is
excuse me, is your polynomial new for so does it give anything new for classical links or it is just new for virtual links?
no, for the classical links, it does not give anything new. Yes, it is just the new stuff concerns the virtual case only. Yes.
And am I right that it neither gives anything new for alternatable?
For alternatable for checkerboard color and virtual links, you mean?
Yes.
It just gives the Jones-Kaufman polynomial for this type of links, for checkerboard-colorable links. That's it. It's just a new formulation of the Jones-Kaufman polynomial for checkerboard-colorable links. Yes, and I discuss this remark here about the alternateness of the Jones polynomial because this approach, this new formulation of the Jones-Kaufman polynomial using the polynomial x actually give an explanation of this phenomena that the the Jones-Kaufman polynomial of an alternating virtual link is not in general an alternating polynomial. So this is what I was explaining. So as I said, we have this knot here, which is alternating. It was pointed out by Bodin and Karimi. It has Jones-Kaufman polynomial equal to minus q to the power of minus 20, q to the power of minus 12, plus q to the power of minus 8. So as we see here, this polynomial is not alternating. So here I have computed this polynomial using our approach. As you can see here, there is some cancellation of monomials that come from different Euler circuits. So here I have minus q, here I have q, here I have q to the power of 5, here I have minus q to the power of 5, I have minus q, here I have q. So this phenomena, meaning that we have Euler circuits of the shadow graph of an alternating virtual link that give us opposite monomials. So this phenomena actually does not occur in the classical case. This stems from the work of Tesla-Waits. And this is actually is the big difference between the two theories, the classical theory and the virtual theory regarding the Jones polynomial of alternating links. So for classical links, if we go see the approach of Tesla-Waits, he works with spanning trees of the Tate graph of the link. If he takes an alternating diagram D, then each spanning tree will give a monomial, and these monomials will all be different, and there will be no cancellation between these monomials. But in the virtual case here, we see that despite the fact that D is alternating, and we're working with the alternating diagram D, and we have the Euler circuits here, there are some Euler circuits that will give opposite monomials, and this will give us some non-alternating polynomial. And actually, under some conditions, we can always have this phenomena in the virtual case. So if we have, for instance, an Euler circuit gamma, and we have 3 vertices U, V, and W, which are pairwise interlacing in gamma. And we have 2 of the 3 markers corresponding to the 3 vertices U, V, and gamma that are the same, or that have the same markers in these states. Then we'll always find an Euler circuits gamma prime which will have the opposite weight of that of gamma, which means that the contributions of gamma prime to the polynomial will cancel out. And this phenomena, as I said, is not present in the classical case. So that's it for me. Thank you very much for your attention.
Okay, thank you very much for your for the talk. Are there any questions or comments? Well, okay, thank you again. And I remind that on Saturday, we start the first online North Congress dedicated to Lewis 80th birthday. You can see this announcement at our site, ktrt-seminars.com. Thank you very much.